Okay, guys, let's start. Mr. Samnang, good to see your face. If possible, keep your camera on, Mr. Samnang. I will give you some additional points. Okay, guys, if you can hear me, let's start. We were talking about chapter 3. That's not so complicated, complex, but still, you need to do some, practice some questions to get, how to say, deeper intuition about these concepts and what is it to be comfortable with working these derivatives. Anyway, so far we have talked about tangents and the derivative at a point, right? Tangent means drawing a tangent line to a curve. Curve means the graph of a function. And the derivative is a function. That means how do we get the derivative of a function? And just we need to evaluate or calculate a special limit and differentiation rules. And in our last lesson, we talk about differentiation rules. That is, how do we differentiate some important functions, and most functions are just the combination of those functions. That's why not directly without using definition we can actually evaluate now almost every function's derivative. Okay, so today we will talk about the derivative as the rate of change, and tomorrow maybe derivatives of trigonometric functions and the chain rule, or maybe let's say if we have time to do also we'll talk about this. I will see. Okay, and after we finish this chapter then you will have a midterm exam, and also most probably you will have quiz on maybe Monday. I'm thinking you will have online quiz, 1 hour quiz. Okay, I'm gonna ask maybe 10 or 12 questions. So okay guys, let's continue that. So here what we have, instantaneous rates of change. Okay, simply instantaneous rate of change means the rate of change of a function at a single point. This is how we name is. Okay, motion along a line. That line is either a horizontal line or vertical line. If you just assume that a point is moving along a horizontal line or vertical line, and how actually we can find the velocity of that point. Okay, and also speed, acceleration, and jerk. You will get introduced with these concepts one more time, and the derivatives in economics and sensitivity to change. And the last, actually, sensitivity to change, I'll just skip this one. If you are interested, you can study. That's just only one example, but we'll talk about these four things. So in section 2.1, we introduce average and instantaneous rate of change. And if you just remember the free fall of a rock, right, from a kind of cliff. And if it just breaks loose, right, actually it starts moving down, and the motion of that rock, or let's say the displacement, was modeled by the equation y is equal to 4.9 t squared, right? And at that time also actually we made some kind of informational introduction to instantaneous rate of change of the displacement, which we call this, well, acceleration. Or I mean, if you're talking about a distance, it is velocity, and also acceleration. Anyway, it's natural to think of a quantity changing with respect to time, but other variables can be treated in the same way. For example, an economist may want to study how the cost of producing steel varies with the number of tons produced, or an engineer may want to know how the power output of a generator varies with its temperature. Anyway, actually, as you see more and more examples, you get more idea about the things, how the calculus is used to solve these kind of problems. So now, once again, let's just start with this definition. What we mean by instantaneous rate of change of a function at a point. All right. Simply, what is it? It is the rate of change of f at a point, at a single point. At a single point to change this, right? The time actually, our independent variable is not changing, it's there. So if you just divide this, it's zero, and we cannot calculate this. And that's why we need this limit concept, so that we can evaluate its limit at that point. So instantaneous rate of change of f with respect to x at x sub 0, that as a single point, is the derivative. So this derivative gives us the instantaneous rate of change. What does it mean? It means that at a single point, at what rate the function is changing. Okay. So for example, the area A of a circle is related to its diameter by the equation. Okay, here D is a diameter, that is 2r, right? And the 2r is equal to diameter, and it's given by this equation. The question is, how fast does the area change with respect to the diameter when the diameter is 10 meters? All right, so we are now talking about the average rate of change of this function over some interval at a single point. Okay, at a single point, at what rate is it changing? Now, actually, this definition is saying that to calculate the average, instantaneous rate of change of some function f at a single point, just we need to differentiate that function. So uh, here, a is the function of d here, right? We need to find when the diameter is d. To calculate this one, and simply this definition is saying that differentiate this and evaluate its value at the given point. So that is solution. Solution here. So derivative of a with respect to d, right? Capital D. That is, what is it? Pi over 4. It's just a constant number. And what is it? That's a power function, right? You take this 2 to the front. Here we have 2 times d to the power of 2 minus 1. That's equal to just 1, which is equal to pi over 2d. Okay. So now to calculate this at when d is equal to 10, that means that I need to evaluate this a prime, right? That means the derivative of a with respect to d when d is equal to 10. So that is equal to pi over 2 times, what is d? D is equal to 10. So that's equal to 5 pi. Okay. So what does it mean actually, this number, this 5p? What do we mean by this? Now, if we draw our circle, okay, and here, suppose that's, well, actually here it is 10. So this one is 5, the diameter is 10 meters. Actually, our circle is getting bigger. The small circle and a bit bigger circle and bigger circle actually just keeps expanding, right? So the question asking that, okay, if it is getting bigger and bigger, okay, the area circle is related to that by the equation. How fast does the area change with respect to the diameter when the diameter is 10 meters? So that means that here at 10, right, here, if you just actually, for example, what does it mean? At a certain rate, if the circle is getting bigger and bigger, right, at actually when the diameter is 10, if I just keep the changing rate constant, let's say it stops changing this, right? So 1 unit change in the diameter of the circle produces 5 pi change in the area of the circle. It means this. Anyway, how about motion along a line? That is displacement, velocity, and the speed, acceleration, and the jerk. All right. So when we just say motion along a line, we mean along a line segment. So line segment, it may be, or just simply straight line. It may be a horizontal line, or it may be a vertical line, right? And suppose that here we are talking about a kind of point that is moving along this point, maybe just moving forward and after the backward, maybe something like this, or kind of something. It's just moving along this straight line. Okay, and suppose that here we have 0. All right, and also here, suppose it's displacement at s. Let's say it is a function of t. Okay, so here, okay, here the position at certain time, all right, that is, let's say here it is, what is it? Here we have s equals f of t. That gives us the position of this particle that's moving along this line when time is t. Okay, so here, if I just move a little bit from this point to this point, okay, because also when time changes, also this particle is moving along this line, and the position changes here. Let's say that is f of t plus delta t, right? So the small change in time, actually just this displacement is from this point to this point. So now, what is the difference here? The difference is, let's say this delta s over delta t. That is displacement over time, right? That is here f of t plus delta t minus f of t over here we have delta t, right? And if you remember, actually this delta t, how do I get this? Delta t is t plus delta t minus actually t, right? Which is equal to delta t. Actually, this ratio, right? This ratio gives us the average speed of this particle over this interval, right? Now, what happens if delta t actually approaches zero? That means that actually this, if this interval is very small, right? If it is very small, that means that actually if delta t goes to zero, then it gives us the velocity of this point, I mean of the particle at one single point. Let's say it is at t. And actually that velocity, right, and is defined as that velocity at t is just derivative of s, this position function with respect to t. That is limit as delta t approaches zero, that is f of t plus delta t minus f of t over delta t. Okay, so that is how we define the velocity of a particle. Now, here s increasing, positive slope, so move up upward. When actually s is increasing, that means that our velocity it should be positive, right? And if it's positive, this is time t, and this one is our displacement function, right? Every time, actually, time is changing, right? So here, that what is it? Our function is moving upward, means that the velocity is what is a positive. It should be upward here, not downward. And this one is down, right? So why is this so? Because this one is velocity positive, means if you look our ratio again, that is f of t plus delta t minus f of t over this delta t. Chichita, is it raining? No, somebody's printing. Okay. Actually, what is this? Actually, let's just take the limit, right? Simply, it's a limit. That is actually our velocity, right? When it is actually negative, negative means that this f of t plus delta t minus f of t, that is negative, right? That means that when I'm just moving, right, here, that negative means f of t plus delta t is less than f of t, right? So if you just like here, when it is positive, we know that how do you find the distance between these 2 points? Let's say this y2 and this one is y1. So actually the distance is, what is it? y2 minus y1. Now here, this f of t plus delta t minus f of t is negative, means that here we have f of t, which is greater than, and here we have f of t plus delta t. Okay, so that means that the difference f of t plus delta t, f of t plus delta t minus f of t is negative. So that means that actually it is just moving downward here. That's why velocity is negative. How about if our move point is moving upward? That means that our velocity is positive. As t changes, increases, and also actually the position changing and it's moving upward. Another definition here we need to know, also actually you know this from high school, speed, right? What is the speed? Speed is the absolute value of velocity, because when you talk about velocity, actually velocity has quantity, right? Magnitude, and also it has direction. Like in our case here, since our particle is moving along a straight line, either horizontal line or vertical line, and also actually the sign actually describes us the point is moving to the right or to the left, or it is moving forward or it is moving backward. So that means that if velocity is positive, that means that it is moving forward. If it is negative, that means that our point is moving backward to the towards the origin or initial point. But we know that actually in cars, right, we have speedometer. It just measures the speed of the car. It's always positive, right? Because you're just actually traveling from home to university or university to home. But even your direction changes, but the speedometer changes the same speed. For example, if you're traveling at a constant speed. And that's why actually speed is just absolute value of velocity, which is absolute value of ds dt. So that means the speed is always positive. It doesn't have direction. It only has magnitude. Now, if you look at this graph, what is it? It is time velocity graph, right? Actually, a horizontal line, it represents time in seconds, and vertical line, it represents velocity, right? V. So now if we look at this, what's going on here? The graph, actually, this velocity, right, as time is changing from 0 to 7. From 0 to 1, our velocity is increasing, right? It's a certain point. That means it is increasing. That's why, let's say, for example, you just actually, you're standing still, and after that, you just suddenly you start moving, right? And for example, if you're driving a car, first you just speed up, right? After you reach a certain limit, certain speed, after that, you just keep at that speed and travel a little bit. Maybe after that, just see a traffic light and just start slowing down. Okay, slowing down. And here, to some reason, as I say here, the speed is in the pink part, it is negative. Negative means actually from this point again, you just make a kind of sudden U-turn and you start moving backward. All right. And again, as I say here, it is moving down, but its absolute value is getting bigger and bigger. That means that again here it is speeding up, right? From the time 3 to 4, 1 second, it just speeds up. Again, from 4 to 5, again, it's slowing down because again, it's moving towards 0. And from 5 to 6, right, it is not moving. Velocity is 0. It means it's standing still. It's at rest. It's not moving. And after that, again, it just starts moving forward, right? And that's how we should understand time velocity graph. Okay, if it is positive, it means that it is moving forward. If it is negative, it is moving backward, right? And if the absolute value of the velocity is getting bigger and bigger, that means it is speeding up. If it is constant, that means it's traveling or moving at a constant speed. Okay. And another two things, using these ideas, I mean, these derivatives, and also we can define two other concepts. One is acceleration, another one is jerk. All right. What is acceleration? Acceleration is a derivative of velocity with respect to time. If a body's position at time t is s equals f of t, then the body's acceleration at time t is simply given by what is the acceleration dv dt and d squared s dt squared. That means that if you differentiate our position function twice, we get acceleration. If you differentiate our position function once, we get velocity. And we have another term, jerk, right? That is sudden movement. You're just sitting and just apply your accelerator to its limit, right? The very sudden movement, okay? This is actually defined as a jerk in physics. Jerk is the derivative of acceleration with respect to time. So that is jerk, that is dA dt, or just simply we are differentiating our position function 3 times. Now let's see one example related to these concepts. Figure on the right shows the free fall of a heavy ball bearing. Ball bearing. Ball bearing means a very heavy ball, right? Made from maybe some kind of iron or metal. Released from rest at time t is equal to 0 seconds. Okay. And what we just say, ball bearing is quite heavy. Okay. So when it is quite heavy and it's very close to the earth surface, so we can just neglect the air resistance. All right. And we know that actually it is displacement, right? Let's say this h of t is given by 4.9 t squared. So question A. All right. How many meters does a ball fall in the first 3 seconds? Right. So how many meters does the ball fall in the first 3 seconds? To find this one again, we know that actually our position function, that's h of t, right? So a is equal to, what is it? Let's say it is s, and in 3 seconds, it's 3. That's equal to 4.9 times, here we have 3 squared, which is equal to, it is 9 times 4.9, that's equal to 44.1, 44.1 meters. So that means that in the first, actually, what is it? 3 seconds, actually the ball travels 44.1 meters. Question B, what is its velocity, speed, and acceleration when t is equal to 3? Right? To find its velocity, we need to differentiate this. What is velocity? Velocity is equal to s prime of t, which is equal to t comes to the front, that is 9.8 t, right? And it says when it is 3. So when it is 3, its velocity is 9.8 times 3. That's equal to 9.8 times 3 is, what is it? 29.4. 29.4 meter per second. Again, this when we just say velocity, actually that gives us the velocity at a single point, because every single point we know that if you just drop a ball, right, that it gets closer and closer to the earth, and also speed actually gets higher and higher and higher. Anyway, and how about speed? Speed is just absolute value of velocity, right? Number 2, here speed is equal to just absolute value of velocity at s3 actually. That's equal to absolute value of 29.4. That's equal to 29.4 meter per second. Okay. And how about the acceleration? And we know that to find the acceleration, we have to differentiate the position functions 2 times. And that means as simple as just v prime t. What is our v? V is 9.8 t. If you differentiate this one more time, acceleration is 9.8 meter per second over second. That is meter per second squared. Okay, so that's one simple problem related to, what is it, this velocity, speed, and the acceleration. Another example, a dynamite blast blow a dynamite blast blows a heavy rock straight up with a launch velocity of 50 meters per second. It's about 175 kilometers per hour. It reaches a height of 49 t minus 4.9 t squared meter after t seconds. How actually high does the rock go? Right? And what are the velocity and speed of the rock when it is 78.4 meters above the ground on the way up and on the way down? And as you see here, the function is, what is it? It's a quadratic function, right? And if you just actually, okay, you're just actually blowing up, right? But if you just draw its graph, the graph is a kind of parabola, right? Here, and here is actually our time, and this one is s, right? So here from this equation, I can just write this as t times, not t, even I can actually take 4.9 out, or, okay, 4.9 t out. So here we have 10 minus t, is it? 4.9 times 10 is 49 t, okay, it is 4.9 t squared. So what does it mean? It means that when t is equal to 0 is equal to 0, when t is equal to 10 is equal to 0. And to find a maximum value, right? Actually, we know this is just a quadratic function. It reaches the maximum value at the midpoint of these 2 points. The midpoint is 5. When t is equal to 5, it reaches the highest point. So here it is 5, the highest point somewhere here, let's say. So that is actually, what is it? The motion of this dynamite. Anyway, so what is the first question? How high does the rock go? That means that we need to find how high does the rock go. Means, as you see here, it's just going up, up, up. Velocity is changing, right? At the top here, right? The velocity is equal to 0. And after that, again, it starts moving down. So that means that we need to find the time where the velocity is equal to 0. So if you just differentiate this, velocity is equal to, it is 49 minus 2 comes to the front, that's equal to 9.8 t, right? Where is equal to 0? So we should find this time. So if you just solve this equation, t is equal to 49 over 4.8, that's equal to 5. So that means that when t is equal to 5, it reaches the highest point, peak point. Now, how high? Now, to find this one, just I need to evaluate the value of this function at 5. It gives us the highest point. So that is 49 times 5 minus 4.9 times 5 squared, which is equal to 49 times 5 minus 4.9 times 25. That's equal to 122.5. 122.5 meters. That is the highest point that this dynamite can reach. Okay, and the second part, let's change the color. What are the velocity and speed of the rock when it is 78.4 meters above the ground, on the way up and on the way down? So actually, 78.5, first I need to find the time. So at what times actually the height of the dynamite will be 78.4 meters. So suppose that actually this is 122.5, it's the highest point. So 78.4 is somewhere here. So now if I just draw a line, right, as see here, at 2 points actually its height will be 78.4. One is when it is going up, one is when it is going down. Now from here, to find these points, let's say this one is T1 and this point is T2. So we need to just solve the quadratic equation. What is it? The first part, that is 49T minus 4.9T squared. That's equal to 78.4. Or if you just take everything to the right hand side, here we have 4.9T squared minus 49T plus 78.4 is equal to 0. 78.4, is it divisible by 78.4? Let me just divide this by 49. What is it? It's 8 over 5. Okay, we have 10 minutes, guys. I will just finish in 5 minutes. Okay, so we have 40 minute limits. Anyway, so how can I solve this? Either we can factorize this, or if you divide all numbers by, anyway, let's just use, what is it? The quadratic equation formula. This delta is equal to 49 squared minus 4 times 4.9 times 78.4. That's equal to 49 squared minus 4 times 4.9 times 78.4. That's equal to, okay, and the square root of answer, that's equal to 147. So that is 147 over 5 squared. Now from here, P1 will be is equal to 4.9 minus 147 over 5 over, what's, it is 147 over 5. Okay. It will be minus y minus 4.9 t squared. It's 49 squared. Okay. 4.9 t squared. Okay. 49 t plus 78.4 is equal to 0. So that is 49 t squared. 49 squared minus 4 times 4.9 times 78.4. That's equal to this. Okay, square root of the answer, 175. Okay. And B minus, all right. Mr. Samnan, why do we get negative answer? Should be positive. 49t minus 4.9t squared. Okay. So 78.4. So it is 4.9t minus 49 plus 78.4. Okay, b squared minus 4ac. It's 147 over 5. And here we have Okay, good. Continue. So that is 49. It is minus b. Our b is minus 49. And here we have 2 times a, 2 times 4.9, which is equal to the T2 will be here. T2 will be 49 plus 147 over 5 over 2 times 4.9. Now from here, the first one, fraction, okay, here we have 49 minus fraction 147 is divided by 5 over 2 times 4.9. That's equal to 2. So that answer is equal to 2. The second one, if it is plus, okay, that's equal to 8. So that means our T1 is equal to 2, T2 is equal to 8. At two different times, the height of the dynamite will be 78.4. Okay, what is the question? What are the velocity and speed of the rock when it is 78.4 meters above the ground on the way up, on the way down? Okay, now that means that we need to find the velocity when it is 2. And what is our velocity function? That is 49 minus 9.82. That is 49 minus 4.8, not 4.8, 9.8 times 2. 9.8 times 2, which is equal to 49 minus 2 times 9.8. That's equal to 29.4. 29.4 meter per second. And at there, speed is equal to velocity, right, is equal to 29.4 meter per second. And how about V is equal to 8, that is 49 minus 9.8 times 8, that is equal to 49 minus 9.8 times 8, that's equal to minus 29.4, minus 29.4 meter per second. And how about the speed, right? Speed there, that is absolute value of V. Again, it's just equal to 29.4 meter per second. All right. So what is the acceleration of the rock at any time t during its flight? So velocity is 49 minus 9.8, right? And its acceleration is minus 9.8. Since actually v of t is equal to 49 minus 9.8 t. Acceleration at any point is just the derivative of velocity function, that's equal to minus 9.8 meter per second square, because always actually it's just what's it, moving downward. So when does the rock hit the ground again? When does the rock hit the ground again? Actually, when is equal to 0, right? And after 10 seconds, right, when t is equal to t, when t is equal to t, actually the rock hits the ground again. Okay, so one more thing, the last 2 minutes, okay, is about what is this derivative in economics. So engineers use the terms velocity and acceleration to refer to the derivatives of functions describing motion. Economists too have a specialized vocabulary for rates of change and derivatives. They call them marginals. Marginal means just the rate, instantaneous rate of change of the production level. In a manufacturing operation, the cost of production, and that is C of X, is a function of X, the number of units produced. The marginal cost of production is the rate of change of cost with respect to level of production. Anyway, here also we have one example, but I will share this with you a bit later because we are running out of time, okay? So that is about one example in economics. Also here, cost function is given here in terms of X. You can just consider this as a function of X. What is the cost to produce 300 first washing machine, right? To do this one, what is the cost to produce this one? Just you need to find this difference, C of 301 minus C of 300, right? And how about what is the rate of change of the cost at X equals 300? That means that you have to differentiate the C, and that gives us actually gives a marginal cost at 300, okay? And just different interpretation, that is how it is used in economics. Anyway, guys, this much is enough for today. Okay, I will meet you tomorrow. Maybe tomorrow we will cover two sections, and next Monday, most probably on Monday at 5 o'clock, you will have 1 hour quiz from chapter 2. Thank you very much. See you tomorrow.